Hey guys, Miss Peterson here, and welcome to our chemistry lecture on acidic and basic solutions. Here, we're going to be learning about reviewing what solutions are. We'll talk about molarity and how we quantify the amount of an acid or base in a solution, and we'll talk a little bit about the pH scale and how that's used. So, let's go ahead and review solutions real quick. What a solution is just a mixture of a solute and a solvent, and that solvent is usually water. So, for example, we have lemonade here, where the solutes, the things dissolved in the water, are the lemon juice and the sugar, and the solvent is water. Now, in terms of chemistry, often we'll be talking about ionic compounds. So ionic compounds, remember, dissolve into their ions in water. So if we look at sodium chloride here, NaCl, when we put solid salt in water, it doesn't stay together as sodium chloride. It dissolved into sodium ions and chloride ions. If we see here, this K2C2O7, C2O7 is one of our polyatomics. It's called chromate. So in our potassium chromate solution, we'll have some potassium or K ions and some chromate ions, some Cr2O7 ions. Okay, so that's solutions. Now, concentration is a measure of how much solute is in solution. If we're talking in qualitative, just describing it, we'll talk about more concentrated solutions that have higher levels of solute per liter of solution versus more dilute solutions that have lower levels. Now, some methods of concentration that we've looked at before are things like percent composition, okay? If you have vinegar that is 20% acetic acid, okay, or 3% hydrogen peroxide, that's telling you what percent of that is the hydrogen peroxide. Okay, we've talked about ppm in the atmosphere and how for every million molecules there are in the atmosphere, they think it's 300 and something would be carbon dioxide. Or we could talk about the mass that we dissolved per liter. But we'll be zooming in on one that chemists used most often, which is molarity. So we have this table here that goes over the number of molecules, okay? Which those are really big numbers. They're just not that convenient to use. So often, or always, we convert it to moles. So a mole is equal to 6.02 times 10 to the 23rd atoms. So 6 times 10 to the 23rd is 1 mole. Divide it by 10, aka take away a factor of 10. Divide it, we'll have 1/10 of a mole. And then molarity is our measure of concentration in moles per liter. So 1 mole in 1 liter, 1 molar solution. So is 10 moles in 10 liters. That also makes a 1 molar solution. Okay, where if we have just this many molecules, which is 0.1 moles in the 1 liter, it's a 0.1 molar solution. Okay, let's go ahead and do some example problems like this. We'll do some together, and then I'll ask you to do some on your own. So first, a 1 liter sample of ocean water contains 7.9 times 10 to the negative 9 particles of hydrogen ions. What is the molarity of the solution? So we're looking for the molarity of hydrogen ions in the solution. So we learned in our last slide that molarity is the moles per liter. But I have this in particles. So I'm going to need to convert it to moles before I solve this out. So let's go ahead and set up for a unit conversion. Okay, the conversion that we're going to use is 1 mole equals 6.02 times 10 to the 23rd particles. So, like always with our unit conversions, we're going to start with our known, 7.9 times 10 to the negative 9 particles. And then that's what I want to cancel out. So I'm going to basically be dividing this by Avogadro's number. 6.02 times 10 to the 23rd particles is how many particles are in 1 mole. Makes it a lot easier to count. Okay, so let's go ahead and plug that into our calculator. That's not the calculator I wanted. Zip. Oh, there it is. Okay, so we got 7.9 times 10 to the negative 9 divided by 6.02 times 10 to the 23rd. And we get 1.3 times 10 to the negative 14 moles. So a very small number of moles. But that's okay. It's a 1 liter sample. It's going to be a small concentration. So next, how many chloride ions, so that's Cl minus, would be in a 1 liter sample of a 2 molar NaCl solution? So remember, 2 molar means 2.0 moles of our NaCl per each 1 liter of water. And we can actually use molarity kind of like a conversion factor, because really we're trying to figure out how much 1 liter of water would have. So we can count that as our known, and this will convert us to moles of NaCl. But for every 1 mole of NaCl, we're going to have 1 mole of our chloride ions, okay? Which I guess you didn't really need to write that conversion, but it's a 1-to-1 ratio. So if I have 1 liter of a 2 mole per liter solution of NaCl, I'm also going to have 2 mole per liter of our Cl minus ions. Okay, cool? Okay, cool. Let's try some more. So these ones I want you to do on your own first. A solution of NaOH is prepared by dissolving 6 times 10 to the 23rd particles of solid NaOH into 0.5 liters of water. What is the molarity of the solution? So what are we going to need to do first? Well, we know molarity is the moles per liter. I know how many liters I have, but I don't know how many moles. But 1 times 10 to the 23rd particles, okay, that, if 1 mole is 6 times 10 to the 23rd particles, we can assume that this is 1 mole. So to plug into our molarity, it would be 1 mole of NaOH divided by 0.5 liters of water, giving us a 2 molar solution. Oh. Ooh, what about this one? If I have 100 milliliters of a 0.05 molar solution, how many moles of solute are there? How many molecules? Well, I gave you this conversion factor. 1,000 milliliters is 1 liter. And then what I like to do is rewrite our molarity to be like a conversion factor. So 0.05 molar means that if you have 1 liter, you have 0.05 moles. Or you could always just rewrite it as 0.05 moles per liter instead of that capital M. Okay, capital M means moles per liter. So let's go ahead and start with the 100 milliliters. If I have 100 milliliters, well, this is in moles per liter, so I have to convert it to liters first. So there's 1,000 milliliters in 1 liter, so that we have the milliliters cancel out. Then we know there's 0.05 moles in each 1 liter. So the liters will cancel out again. We plug it into our calculator. Okay, we got 100 divided by 1,000 times 0.05, which gives us 0.005 moles. And then if we wanted to convert to molecules, we would multiply it again. 1 mole is 6.02 times 10 to the 23rd molecules. So if I multiply that number by 6.02 times 10 to the 23rd, I get 3.01 times 10 to the 21st molecules. So 0.05 moles of the solute, which is equal to that many molecules. Okay, cool. Okay, cool. So let's go ahead and talk about pH. So the pH scale is used to categorize things as either acidic or basic. So neutral is given the pH of 7, and then acidic solutions are less than 7, and basic solutions are more than 7. In order to tell the pH of something, we'll typically use an indicator, which is something that changes color based on pH. A really common one is bromothymol blue, or BTB, which is yellow in acidic solutions, so for pHs less than 6, and blue in basic solutions for a pH more than 8. And then between 6 and 8, it's green, and it fades in that green for really more fine precision when doing those pHs that are right around neutral. So what is the pH scale actually measuring? Well, it's a concentration. It's a concentration of ions, specifically the number of hydrogen ions. Now, it's a logarithmic scale. The actual formula, which we're not going to use in this class, is pH is the negative log of the molarity of the hydrogen ions. And sometimes you'll see it written as hydrogen ions, but if that hydrogen ion bonds with a water molecule, we can also write it as H3O+. And these two are used kind of interchangeably. Now, pH is related to hydrogen, which is related to water. Okay, water can act as an acid or a base. Acid or base. Because it both produces the H ions, which are characteristics of an acid, and the OH ions, okay, called hydroxide, which is characteristic of a base. So if we see here, this is the number of hydrogen and hydroxide ions in 3 milliliters of water at the different pH levels. So you can see they're really big numbers. That's why we use this logarithmic scale, because 0 through 14 is a lot easier than 10 to the 21 to 10 to the 7th. Yep. So our acids will have more hydrogen than hydroxide. So at pHs less than 7, you can see these numbers are bigger than these numbers. Where for bases, pH more than 7, we're going to have more of those hydroxide ions, those OH minus coming from it. And you'll typically see that in its chemical formula. Yep. Okay, cool? Okay, cool. Let's go ahead and do some practice. So these ones, they're not calculations. I think you can figure it out. Based on the descriptions, are each of these solutions acidic or basic? Go ahead and classify them. And let's review. A solution with a pH of 2.8, that's less than 7. It's acidic. Where pH of 11 is basic. If you are equal in hydrogen and hydroxide, that is a neutral solution. And that's why water's neutral, because it breaks into H plus and OH minus in equal amounts. If we have more H plus molecules, 10 to the negative 7, that's a bigger number than 10 to the negative 8. So 10 to the negative 7, okay, this should say moles, not molecules. Okay, this should say moles. So if we have more moles of hydroxide, then we are going to be basic. Where if we have more moles of hydrogen, that means we're going to be acidic. Okay, cool. Okay, cool. Go ahead and practice these skills.